Hello friends, today we are going to see how to count the number of binary search trees which can be formed with given n distinct keys. So let's see here, if you are given one key and that key is 5, then obviously you can form only one tree, and in that one binary search tree the node will be that key itself, that is 5. Okay, now if you are given two keys, that is n equal to 2, and the set of keys is 5 and 6, that means there are two keys, that is one is 5 and other is 6. Then how many binary search trees can be formed? See, if we make 5 as the root, then 6 will be on the right side of 5. As you know, in a binary search tree, the number which is less than the root is on the left side and the number which is greater than the root is on the right side. If we now make 6 as the key, then 5 will be on its left side because 5 is less than 6. Okay. Now we can say that for n equal to 2 there are two binary search trees. So let's fill the values in this array. So for n equal to 0 keys, how many binary search trees can be formed? 0 binary search trees. Obviously, if there are no keys, then no binary search trees. So for 0 binary search trees. Then for n equal to 1, how many binary search trees can be formed? One binary search tree can be formed. So I write here 1. Now for n equal to 2, how many binary search trees can be formed? Two binary search trees can be formed. So I write here 2. So now let's calculate the number of binary search trees for n equal to 3. So there is a set of 3 keys and the keys are 5, 6 and 7. See here, just for your understanding, I have written the keys in sorted order. But it is not necessary that these keys should be in sorted order. Whatever the order is of the keys, the number of binary search trees will be same for the number of keys equal to 3. Means whatever is the order or whatever are the keys, means even if here it is 100, 150, 200, then also the number of binary search trees are going to be same. Or even if it is like 7, 5 and 6, then also the number of binary search trees are going to be same. Just for our understanding, we have written the keys in the sorted order, which makes it easy for us to draw the binary trees. Okay, so the only thing we have to focus on is that the number of binary search trees when n equal to 1, n equal to 2, then n equal to 3, n equal to 4. So we have to focus on this, the number of keys. Okay, and obviously these keys must be distinct, means they should not be repetitive, means it should not be like 5, 5, 7. Yes, then there will be a change in number of binary search trees. So the keys should be distinct. There should not be a repeated key in a set. We are going to derive a formula for number of binary search trees in which there are distinct keys. Okay, so let's go ahead. For n equal to 3. So if we take 5 as the root, then 5 is the root. Obviously 6 and 7 are both greater than 5. So they can be on the right side. Okay, this is one possibility. Then one more possibility is 5, then first 7 comes and then 6. This is another possibility. See, that's why I told you it is not necessary that we should follow this order. We can access the elements in this set in any order. suppose first 5 comes, then 7 comes, and then 6 comes, then this one is also a possibility. Then the next thing is with 6 as the root. So if 6 is the root, then 5 will be on the left side and 7 will be on the right side. So as 6 is the root and this is the sorted order, that is 5, 6, 7, there is only one possibility. Now for 7, if 7 is the root, 5 and 6 are on the left side. So it will be like 5 for 7, 5 is less than 7 and 6 is greater than 5. Or for 7, if 6 comes first, then 6 is less than 5, and if then 5 comes, so 5 is less than 6. So these are the two possibilities. So total there are 5 binary search trees which can be formed with 3 distinct keys. Okay, so let's write it in the array. For 3 keys, 5 binary search trees are possible. So let's now see for n equal to 4, means what are the number of binary search trees for n equal to 4. So the set of keys is 5, 6, 7 and 8. So here let's take 5 as the root first. 6, 7 and 8 are greater than 5. Again 5, take it as the root. Now as we have fixed 5 as the root, we just have to access the variation of 6, 7 and 8. How many variations are possible for 6, 7 and 8? Obviously we know for n equal to 3, how many binary search trees are possible? 5 binary search trees are possible for n equal to 3, because 5 is fixed. And what we are going to next is that we are going to make a variation of these 3 keys. So let's see that. So for 5, now 6, 7, 8 can also be like 6, 8 and 7. Okay, this is one possibility. Then again 5 as the root, then it can be like 7, then 6 and 8. This is another possibility. Then again 5 as the root. Okay, then 8, 7 and 6. Right, and again 5 as the root, then 8, 6 and then 7. This is also one possibility. See, so these are the 5 binary search trees when the root 5 is fixed. Okay, when the root 5 is fixed, that means as this number matches to the number of binary search trees when n equal to 3, that means we have just done the variation of these 3 keys. We have just put them in different places, right? We have just accessed them in different orders. So what I mean is that just fix 5 as 6, 7 and 8 are greater than 5. Just write it like this: 6, 7 and 8. Okay, and we will directly get the number of binary search trees for n equal to 3. These are the binary search trees when 5 is the root. Then when 6 is the root, see, 5 is on the left side. So this is one set, and 7 and 8 are on the right side. Okay, so n equal to 1 and n equal to 2 means what? Invisibly here it is n equal to 0. See, n equal to 0, because there is no key on the left side, because 5 is the least element. As this is the sorted order, for 5 there will be nothing on the left side. because all elements are greater than 5. So if we take a sorted set, then first possibility is that if we make the first element as the root, then n equal to 0 on the left side and n equal to 3 on the right side. Okay, then for 6 as the root, means for the second element as the root in this ascending order, for the second element in this ascending order, if we make that element as the root, then there will be one element on the left side and two elements on the right side, because in this order there is one element which is less than 6 and two elements which are greater than 6. Again, let's make 7 as the root. Then there will be two elements on the left side, 5 and 6, and one element on the right side, that element is 8. Okay, so n equal to 2 and n equal to 1, right? Now the final thing, 8 as the root. Okay, so if we make 8 as the root, then there will be 3 elements on the left side, that is 5, 6 and 7, n equal to 3, and 0 elements on the right side, so n equal to 0. This is the right side. It will be n equal to 0 because there is nothing greater than 8. So now let's calculate the number of binary search trees. See, n equal to 0 and n equal to 3 means obviously as this is there will be no binary search trees with this variation on the left side. Only the variation on the right side should be considered. So what is the variation on the right side? For n equal to 3, how many variations are possible? See here, for 3, 5 variations are possible. So 5 binary search trees can be formed with 5 as the root. I have shown you by forming the binary search trees, which was the proof for that. Okay, now for 6 as the root, if one element is on the left side and two elements on the right side, see, for n equal to 1 there is only one possibility, right? And for n equal to 2 there are two possibilities. Okay, then for 7 as the root, for n equal to 2 here on the left side there are two possibilities, and for n equal to 1 there is one possibility. Again, for 8 as the root, for n equal to 3 there are 5 possibilities, and for n equal to 0 there is no possibility. Now we are going to derive the formula. So see, how do I do that? Now what we say is that suppose 5 is the root, or 6 is the root, or 7 is the root, or 8 is the root. So I am using the OR symbol, means I have to add the possibilities. See, this is OR. How I am doing it? Suppose 5 is the root, or 6 is the root, or 7 is the root, or 8 is the root. As I am using OR, if you know the combination formula, then you have to add the possibilities for that. Okay, and inside what I am doing, I am dividing the keys. So see here, 0 keys on the left side, 3 keys on the right side. So for n equal to 3, 5 possibilities are there. Or when 6 is the root, n equal to 1 on one side and n equal to 2 on another side. Okay, n equal to 1 on left side and n equal to 2 on another side. I am using AND, so the possibilities will be multiplied. Okay, now so 1 into 2, 2 possibilities. Now when 7 is the root, then n equal to 2 on one side and n equal to 1 on other side. So 2 into 1 plus, see here, when n equal to 3, that is on left side, and 0 on another side. So there is no possibility for n equal to 0. So there are only 5 binary search trees possible. So see here, 5 plus 1 into 2, that is 2, and 2 into 1, that is 2. So 5 plus 2 plus 2 plus 5. So there are total 14 binary search trees possible when n equal to 4. Now we are going into the final stage for n equal to 5. So for n equal to 5, I will write the formula totally. So now let's see for n equal to 5. So the set of keys is 5, 6, 7, 8 and 9. So for n equal to 5, in this set of keys, if we make 5 as the root, then there will be 0 keys on the left and the remaining keys on the right, that is 4 keys. So n equal to 4. Okay, then if we make 6 as the root, see, there is no need of writing this set and all, because the set and the values in that set does not matter, because what matters is the value of n, that is n equal to 3, 4 and 5, that matters. So we just write the number of keys now. For 6 is the root, there will be obviously 1 key on the left and 3 on the right. So n equal to 1 and n equal to 3 on the right. So here n equal to 1 on left and n equal to 3 on right. Now for 7 as the root, n equal to 2 on left and n equal to 2 on right. Okay, then for 8 as root, see, n equal to 3 on left and n equal to, see here, 1 on right. And for 9 as the root, again n equal to 4 on left and n equal to 0 on right. Okay, so this is the way in which we have to find out the number of ways in which these keys can be arranged in binary search tree. Now, as you know, we say like 5 is the root for the binary search tree, or 6 is the root, or 7 is the root, or 8 or 9 is the root. So it comes plus here. Okay, and for n equal to 0 keys, there is no possibility of a binary tree. So if we say like there are 0 keys on the left and 4 keys on the right, okay, if we say like that, then it will be a multiplication of 0 into n equal to 4, so the value is 14. It will be a multiplication of 0 and 14, so that will become 0, but we don't want that. So for dynamic programming, for memoization, we have to hard code the value of 0th index as 1. See, this is hypothetical. This base condition, see, this is the base condition, and this is hypothetical because there cannot be a binary search tree with 0 keys. But just for our convenience, just for our programming, we write as for n equal to 0, there will be a one binary search tree. And you can say that that binary search tree is a null binary search tree. Okay, is a null binary search tree. You can say that, and you can count it as one binary search tree. So that is the base condition. Now we can write 1 here. And one more interesting thing, look at the distribution now. 0 and 4. Okay, 0, 4. Then for 6, see, for 6 it is 1, 3. Means add in 0 and subtract from 4. Okay, so that is plus 1 and minus 1. 0 plus 1, 4 minus 1 equal to 3. Okay, again follow the rule. Here for 7, 1 plus 1, that is 2, and 3 minus 1, that is 2. Okay, plus 1 minus 1. Right? Now, all these things I am telling you for programming, for the formula for coding. And for 8, see, plus 1 minus 1 means 3 and minus 1 means 1. Okay, and finally for 9 as the root, 3 plus 1 is 4 and 0. Now let's calculate the number of binary search trees. So for 1 key, how many binary search trees are there? 1. Into, for 3 keys it is 5. Then for 2 keys, how many binary search trees are there? 2. And again for 2 keys, 2. For 3 keys it is 5. Into, for 1 key, 1. And for 4 keys it is 14. Into, for 0 keys it is 1. Okay, so it is 14 plus 5 plus 4 plus 5 plus 14. So 14 plus 14, 28, plus 5, 33, plus 5, 38, plus 4. So that is equal to 42. Okay, so there are 42 binary search trees possible. Now let's write the formula. So see here, this is the main part of the code. As you know, for number of keys equal to 0 and number of keys equal to 1, we hard code the values as 1 and 1. So that is initialized here, n of 0 equal to n of 1 equal to 1. Means in this array we have initialized the values for index 0 and 1 as 1. Now inside the for loop, now see, for I equal to 2 to n, that means suppose n equal to 5 here. So we want to find out the number of binary search trees for n equal to 5. So let's just clean this value and now we will find out this value again. So see, I equal to 2 to 5 means for calculating the value for 5th index, we need to calculate the values from index 2 to 5, because we are going to make use of the values of index 0, 1, 2, 3 and 4 for calculating the value of index 5. Index 5 means the number of binary search trees for n equal to 5. So this is what is dynamic programming, means we are memorizing the values while we calculate the values. Means for I equal to 2, then 3, 4, so we will memorize these values here, and for calculating the value for 5th index we will use the values of these indices until the 5th index. Okay, so let's see how do we do that. So now just assume that we have calculated the values up to index 4, means I is now 5. So I was first 2, then 3, 4 and now I is equal to 5. So value of I is 5. So we just first initialize n of 5 equal to 0. So we initialize n of 5 equal to 0 and then we go to the sub problems. So for j equal to 0, j is less than I, j plus plus. Now as you know, we have to add the values. See, here we have added the outputs of each distribution. Distribution means 0 keys on left side, 4 keys on right side, then 1 key on left side, 3 keys on right side, 2 keys on left side, 2 keys on right side. So this is the distribution of left and right side, and we have added the values of those distributions. So that is why it is n of I equal to n of I plus, that is here plus equal to. Okay, now this is an important line. See, n of j into n of I minus j minus 1. So let's put I equal to 5. Okay, and this loop is for j equal to 0 to j is less than I, and I is 5, so j is less than 5. So j will go from 0 to 4. Okay, j will go from 0 to 4, means 0, 1, 2, 3 and 4, because j is less than 5, so 0 to 4. Now first thing is n of j. So for the first iteration, j is equal to 0. So n of 0 into n of 5 minus 0 minus 1. That means 0 into 4. 5 minus 1 is 4. That is what is written here. See, 0 and 4. So as you know, we multiply these two values, the 0th index value and the 4th index value. We multiply these values. Okay, so the first distribution is 0 on left side, 4 on other side. That is here 0 on left side, 4 on other side. Now go in the next iteration. Now j is equal to 1. Okay, now j is equal to 1. So n of 1 into 5 minus 1 minus 1. So that is 5 minus 2, means it is 3, and this is 1. So 1 and 3 means n equal to 1 on left side and n equal to 3 on the other side, that is here. Okay, again for 2 on one side and 5 minus 2 minus 1 means 2, so 2 on the other side. So I will write it here, 5 minus 2 and here 2. So 5 minus 2 minus 1 means 5 minus 3, that is equal to 2, and 2 here. So 2 means we have distributed 2 on left side, 2 on other side, and we are going to multiply these two values. As you know, the value for second index is 2 and again second index is 2, so we multiply them. We multiply them because it is a AND operation. Okay, now similarly for 3 it becomes 3 and 1. 5 minus 3 minus 1 is 1, and 4 it becomes n of 4, and 5 minus 4 minus 1 means 0, that is 5 minus 5, so that is 0. So 4 0. So in this way we have distributed the numbers, means we have written a program which takes care of this distribution. Okay, now we jumped directly to the 5th index for calculating the values. I explained it just as an example. Now in my next video I will explain the complete program for n equal to 6. So I will explain from I equal to 2 to 6, means I equal to 2, 3, 4, 5 and 6. So for each I will explain this code, how this code works. Hey friends, please subscribe to my channel as I post algorithm videos every day. And if you want a video on any particular topic, then please mention in the comment below. Thank you.